I'm Sölvi, and I'm gonna give you an introduction to what we call device-related transfer functions, or in short, DRTF, which now, from this day, you can simulate in Treble. And the reason you want to use a DRTF, as Daniel briefly mentioned, is, for example, you make a simulation. It can be expensive, take some time, and then afterwards you realize, oh, maybe I don't want this person in the simulation to have glasses. I would rather that that person has headphones. And then you can, basically without rerunning a simulation, you can switch out the device in the simulation. And we've done this study in a fully furnished room where we did measurements. You can see the rendering of the room on the left here, and we placed this Keymar mannequin into the room. We then ran a simulation where there was no Keymar inside the room, and then in post-processing added the Keymar with like binaural microphones into the simulation in post-processing using a DRTF. And here you can see how nicely this worked, that in blue you have simulation data, and in orange you have the measurements for the right and left ear. And you can see here the frequency response as well, and you can see that these add up really nicely. And I want to give you a brief introduction to how we treat these DRTFs inside our simulations. So we have these two things. We have what we will call the room response, so what happens inside the room that we want to simulate, and that's what happens inside the simulation. This can be a wave simulation, it can be a hybrid simulation. And then at a spatial receiver location, and around that location, we do some array processing to kind of capture the effects of the room around that location. And then while we do that, we keep our DRTF or transfer function kind of on the side. We then take this array processing results and project it onto an orthonormal ambisonics basis, and we do the same for the DRTF. And then in post, you have the effect of the room, you have the effect of the device. You can rotate the device any way you want, and then add them together, and at the end you come out with this rendered signal, which would be the same as if you would have included the device in the simulation from the beginning. And the nice thing about this is that now in geometrical acoustic simulations, it would have been hard to include the device from the beginning. But this way you can actually include it in both geometrical and wave-based simulations, and you don't need to rerun a simulation to switch out the device or rotate it or whatever you want. And now, from today, you can create the DRTF in Treble. You've always been able to import the DRTF using measurements, but now you can do it with simulations. So in order to create a DRTF, the information we need is the response at the microphone location or the device location from different angles, and ideally from hundreds of different angles. So in a simulation setup, theoretically we would need to do individual source simulations from hundreds of different angles, which would become very expensive because these are many simulations. But thankfully in wave physics we have a thing called reciprocity, which means that this scenario that we have in this illustration is equivalent to this one here, where we're listening at hundreds of different angles, and we only play the sound source from the intended microphone locations. So this is what we do in the simulation. We do a simulation from the center, from the actual microphones on the device, and listen at a sphere around the device. Then we take these results and we encode this into ambisonics, as I mentioned before, to get this on like an orthonormal basis that we can then put into the effects of the simulation, of the room simulation that we had before. And we have different ambisonics orders. We offer up to order 32 in ambisonics, and I want to briefly show why ambisonics order matters. And for that, I have this little example where I have two plane waves propagating in perpendicularly at 1 kilohertz frequency, and we can combine them into this nice little checkerboard we have here. And then what I'm going to do is I'm going to place an ambisonics receiver in the middle of this field and try to reconstruct the field for different ambisonics orders. We'll start here at ambisonics order 4, where we managed to resolve the wave field quite decently at the center, but as we go further away, our solution is quite bad. But if we increase the order, go up to order 8, now we can see that the area is getting a lot bigger, and up to 16 we almost resolve the entire wave field that we have here. And this was a sphere of 1 by 1. But on the other hand, we also have the frequency dependency. And if we now increase the frequency of the wave field up to 2 kilohertz and keep the ambisonics order fixed, now we resolve a smaller area. So it's a balance between what frequency you want to resolve, how big your device is, things like this, which helps you decide what kind of ambisonics order you need for your DRTF. We have all sorts of tools in the SDK which help you decide on these things, and I'll show this later. So if we now look at this fictional device here, what you would have to keep in mind if you want to create a device for something like this is that ideally you want to be able to resolve the wave field kind of around the device in a sphere that encloses the device. It doesn't have to be bigger than the device, like in this case, but it has to, ideally, if you want to capture the full effect, it needs to be around the entire device. This device has a length L, and this is sort of the rule of thumb formula that you can use to decide on which ambisonics order you use for which frequency you want to resolve. So N here is ambisonics order, speed of sound, and then we have frequency here. But it's not only this that the ambisonics order does for you, it's also that with a higher ambisonics order you can capture a more complex pattern. So here for the same microphone with different ambisonics orders, you can capture a different level of complexity of the response of the microphone. And I have an example here, which is not for this device, it's for a KEMAR, where we render the ear, one of the ears, with on one hand ambisonics order 4, and on the other hand ambisonics order 16. And you can see that the ambisonics order 4 is kind of like low pass filtering spatially compared to the ambisonics order 16, where you capture much more detail. So now we're in the SDK, and in this demo I'll show you some tools that we have to estimate the required ambisonics order for your device, and I'll show you a simple interface of how to set up a device creation simulation, which will also have an intensive guide on the documentation website upon release. And then lastly, I'll show you how you can then at the end analyze the results of your device and how the device you can expect it to perform. We start by initializing the SDK and making a project, and then now, like basically from this picture that we had in the slides, we can I have a tool here where you can plot the ambisonics order, what you can expect to resolve from the ambisonics order. And here what we have is on the x-axis we have the maximum frequency that you can expect to resolve, and on the y-axis we have the radius of the enclosing sphere of the entire device. And for example, for order 8 you can expect here at 6000 Hertz that you can resolve a sphere of radius about 7 centimeters. But if we go up to order 16, you can see that it goes higher, and up to order 32 we can expect at 6K to be able to resolve a sphere of almost 30 centimeters. And this is something that you can use beforehand to kind of estimate what you want, and it's using the rule of thumb formula I mentioned in the beginning. Another tool which is it's the same but presenting the information slightly differently. Here you can print the guideline table for if you know the radius of your device, and then the ambisonus order that you expect to use. You can print the table like this, which tells you that for whatever ambisonus order you can expect to resolve this frequency. And for this demo, I'm going to be using a device that has an enclosing sphere of a radius of about 20 centimeters. So it looks like we're going to have to use 32nd order to properly capture the device. And here I'll show you how to set up a simulation for something like this. And all you need to do is to have a file that you, with your CAD file, and you could add this to the SDK. I already did it, so I'm gonna just get the model by the name, and I'll plot the geometry. This is how the device looks. It's kind of a simplistic device, and I'll place microphones here to the two sides, the right and left, here one slightly to the back and one at the front. And this is what I define here with these device microphone placements. I define these 4 points. I define the frequency of my free field simulation and the ambisonus order that I want, and then use this to set up a simulation. I've already done this, so I'm not going to do it now. And then what you have to do once this is done, it can take up to like 2 minutes usually, and then you can add the simulation to your project and start it. And you just wait for it to finish. But I already did, so I'll just get the simulation and plot it. It takes a few seconds to get the simulation and put up the plots, and we have it here. In the meantime, I'll keep this thing running. So here I have the simulation. You can see the sphere that we have, and all those dots here, those are receivers. And inside here we have the device. See, we have a microphone here at the front, one at the center, slightly further back, and then 2 to the sides. So when we have the results of the simulation, we can use those to create the DRTF. And afterwards we add the device to the library, which then does the ambisonics fitting. And when you create the device, you can pick the ambisonus order. It has to be equal or lower to the one you used when you made the simulation. And what I've already done is I've created the same device for order 32, 16, and 8. And I have those here. And then I'm going to show you a little plotting tool that we have to analyze the results. So here what we can do is we're plotting the transfer functions of the different microphones based on the spherical harmonics or ambisonics. So here we can look at transfer functions for the different microphones that we have, and we can look at different angles and see how the response of the microphones changes. Then we can also go back to and see the spherical harmonics fit. What you can see here is how the energy is distributed in frequency on the x-axis and in ambisonus order on the y-axis. And here on the top left and top right microphones, we can see kind of how most of the energy is along this line here. It's much deeper than the one for the top center microphone, and that's because the top center microphone is very close to the origin, and then we need like lower ambisonus order to render higher frequencies. And then what we also see this kind of faint area here, which relates to the size of the device and the effect of the actual device, like diffraction around the edges and things like this. And we can see that for the top left and top right microphones, we definitely have some energy coming up to order like 25, 26, but less. But most of the energy is close to order 16. What we can also do is plot this polar pattern. So here we're plotting from above, and we're plotting then as we go around the axis as we go around this axis, we plot the response of the microphones. And we can see here how the microphones on the top right and top left, they're basically symmetric in that plane. And we can add here the microphone at the front, where you can see how it's very sensitive when the wave is coming from the front, but less so when it's coming from the back, which makes sense. But to analyze how nicely you manage to fit the input transfer functions, you can click this check mark here to compare to the input, and you can see here for this particular one with 32nd order rendering, the fit is basically perfect up to the entire frequency range. And then what we can do is check on the other devices, because I made for lower ambisonus orders, like for order 16, where we capture most of the energy, but probably not all of it. Can plot this again. Here we see the spherical harmonics that they are kind of, we're obviously not getting all the energy because it's kind of stops here. And if we plot the transfer functions and compare to the input, see for some angles it's happening, it's working pretty well, but for some of them definitely less so. See here it's diverging quite a bit, and especially for angles coming from below. If we look at the front microphone, it's quite off, but very good for the lower frequencies. And then like we can continue this story, go even further, and do the compare to input again for this one. Again here it's quite obvious that we're cutting off a lot of the energy. Then if we compare to the input, we're already off quite a bit. We're not catching this dip here at all, for example. And so this kind of demonstrates the effect that it has to properly resolve the whole sphere using very high order ambisonics, like the 32nd order ambisonics. But at the same time, it also shows you that, like, if you're more interested in the lower frequencies, then the other thing can be okay. So that's it for me. Thank you.